I give you the diagram for the motor equivalent circuit. So first diagram with the sensei.
What volume number is this?
G43 and 45. So that will be the RS and the AS as sensei. So that will be the resistance RC. This is full resistance. This is a HM. So full inductive resistance reactance. So this similar to this side will be the primary side. So this is the ES. And this one will be the ER. So then will be the resistance RR, rotor resistance, and then rotor winding is inductance HR. So we call like this. That is the AC. So supply mode is a VS. Okay, this is for the sensing condition. Sensing conditions are the voltage will be this ES here, this is ER here. And then we also calculate for the energy slip. So energy slips are, this is a resistance. So RS and the HS here. So that will be the ES. And this will be the SER. SER means slip multiplied by rotor resistance. And this is RR. And this is the SHR. So this one we use RC and HM. So this is for the any slip. The supply voltage is BS. So any slip. Any slip we can collect circuit like this. So this circuit can also be modified. This circuit is similar to that one. This one is the IS is supplied here. And full resistance RC, full inductance is HN. We connect. And this one we use stator resistance RS. And stator inductive reactance HS. And this one we use ES. And also similarly this side we use ER. ER and then this one we use RR and then HR. So means the currents are flowing outward. Yes, this is outward. So this is what we can run. And also this one with this one with the rotor equivalent. Rotor equivalent electrical diagram. So this is RR into 1 minus slip divided by S. So S means a slip. So in this case we get the thing. So ES is a stator voltage. Stator voltage. ER means a rotor voltage. And RC means a core resistance. And HM means a core inductive reactance. Okay, so this is means rotor resistance, rotor winding resistance. And it is HR, also the rotor winding inductive reactance. And also that we can also calculate for the RS, so stator winding resistance. Stator winding resistance. And HS means that stator winding is inductive reactance. So those are the the typical characteristic of the stator and the rotor, and also we can calculate for the S. S means slip. So those are the information, the equivalent circuit. So that we can also calculate for the current. So current flow in the motor, IR formula can calculate SER divided by RR plus JSHR. In the resistance is the real term and inductive reactance is the imaginary J term. And also that this one is similar to this equation. This is equal to the ER divided by RR by S plus JHR. So this one also is similar to the ER divided by RR plus JHR plus RR into 1 minus slip divided by slip. So because of this one, RR means rotor winding current. So this is the RR, rotor winding current. So those is we calculate for the three-phase induction motor. So calculation to get out. So this means that we can provide the winding resistance here. So this is the RS plus RR just by S. And this is also the HS plus HR diagram for the motor equivalent circuit. So first diagram with the stem state.
What volume number is this?
G43 and 45. So then we use the RS and the AS as stem state. So AS means straight out winding is inductive reactance. We combine the stator winding and the rotor winding together. So this means that we can provide the winding resistance here. So this is the RS plus RR just by S. And this is also the HS plus HR test. And this one we use the co-resistance RC and co-inductive reactance HN. So supply voltage we use the VS. Okay, so this one how to calculate the RR dash. So RR dash by S is equal to current ratio square multiply RR by S. So rotor winding resistance divided by slip and multiply the time ratio square, you got the R dash by S. Similarly, HR dash. HR dash you can also calculate time ratio. Time ratio square multiply HR. Then you can calculate HR dash. So time ratio is you can calculate the stator turns divided by rotor turns. So time ratio. So stator turns per phase divided by rotor turns per phase. Stator turns per phase divided by rotor turns per phase. Then we got the turn ratio. And similarly, you can also calculate the IR dash. IR dash you can also calculate the formula is VS divided by square root of RS plus RR dash by S square plus AS plus HR dash square. So by this way, you can calculate the rotor current. So this rotor current is an IR dash here. You can calculate by this way. 440 volts 4 poles 3-phase 50 hertz living induction motor. Each winding has a mesh connected in the stator and rotor winding is a star connection. So this is a sliding motor. Sliding motor means that because the rotor and stator winding, stator is connected in star and sliding in delta, meshing in delta. So this way we have stator. So So that will be supply voltage at 440 volts. This supply. Supply voltage 440 volts, and then this one will be the rotor. So this is the rotor winding. Rotor winding, this one will be the EI square to. So output rotor voltage is a straight line 440 volts, and rotor winding is at 218 volts. So 218 divided by 216 volts. So 216 volts. So divided by root 3. So this is the rotor winding. 216 by root 3. So that will be the voltage across the slip ring. The 3 slip ring, that they are connected like this. We connect like the lower slip ring. Okay, so firstly we have to calculate the turn ratio. Turn ratio means we have to calculate for the stator voltage per phase and the rotor voltage per phase. So this is called the turn ratio. Turn ratio is Ks. So this is the ES per phase divided by ER per phase. So ES by phase is stator voltage 440 volts. ER by phase is 216 divided by root 3. And then you call the phase at 240 divided by 126. So this is a 3.49. The turn ratio Ks is 3.49. And after that you have to calculate for the calculate rotor current. So rotor current means I already given you the formula to calculate rotor current. I is equal to the ER by RR plus J is SHR. So this is the current. So rotor current IR you can calculate. ER by RR plus J SHR. So this is also equal to the ER by square root of RR by S plus J HR. This is the same as ER divided by square root of RR by S square plus HR square. So this is for the IR you can calculate. So IR you can calculate, you substitute here. So ER is you substitute it per phase ER by phase. So this is ER by phase. So 216 by root 3. So this is 126 square root of. So rotor resistance. So rotor resistance is this problem. Rotor resistance given. Rotor resistance per phase is 0.05 ohm. So this is for the rotor resistance per phase already given. And rotor reactance per phase is 0.25 ohm. So the RR and the HR we can substitute. So RR is we can substitute at 0.05 ohm. HR is at 0.25 ohm. So 0.05. So slip is 1. Because the slip is a 1 because of this motor has a standstill connection. Standstill connection means that when the motor, before motor starting, when you put the supply, this slip motor at the supply connection, starting connection, you need to short circuit the oscillator. Just for the short circuit for starting. All the cylinders need to be short circuited to start this motor. And therefore the starting condition, all the short circuited. So that as you can substitute, the HR value you can substitute. HR value is 0.25 ohm plus 0.25. The whole square. So by solving this one, the IR will be the 504 ampere. So this is for the motor rotor current we can calculate like this. Okay, so this is for the motor calculation. And also we also need to rotor current and stator current. Stator current means you have to refer the rotor current to the stator side. So this is you have to stator current is the formula. This is for the rotor current. This is for rotor current. And another one is stator current. So stator current formula is IR K. So this is the stator current. The formula is a BS square root of divided by square root of RS plus RR dash by S square plus AS plus HR dash square. So this is for the theta current we can calculate. Okay, so before you calculate the theta current, you need to substitute. So the RR dash by S you can substitute. RS is already given. So RS is theta resistance. Theta resistance already given. The theta resistance are the 0.6 ohm and 3 ohm. So theta resistance 0.6 ohm, theta bar reactive bar phase is 3 ohm. So RS is 0.6 ohm. And so AS is 3 ohm. And similarly, rotor resistance. So rotor resistance bar phase. So this is RR dash you can calculate. RR dash by S you can calculate. Then we just KS square multiply with RR by S. So KS we substitute 3.49 square multiply with RR is 0.05 divided by 1. So then we just 0.609 ohm. And similarly, HR dash. So HR dash you can calculate KS square multiply HR. So this one with the KS square is 3.49 square multiply HR is 0.25. So this HR will be 3.045. So then we got the RR dash by S and HR here. And then you now substitute IR dash you can calculate. So VS is 444 theta voltage. So theta voltage of phase also the 444 because the star and theta voltage line voltage is the same as the phase voltage. So because of this one VS bar phase you can substitute as 444. And RS dash by S HS HR dash you can substitute now. So the square root of 440 divided by square root of and RS you substitute 0.6 plus R dash by S. R dash by S 0.609 square plus so AS is 3 plus HR dash. So HR dash is 3.045 square. So by solving this one, the theta current we got, the theta current will be 71.7242 ampere. This is for the theta current. And after that, you can also calculate the theta power factor. So theta power factor formula is the cos tangent inverse AS plus HR dash divided by RS plus RR dash by S. So this is for the theta power factor. So we substitute here. So this becomes a cos tangent inverse AS and HR dash. So AS is a theta resistance 3, HR dash is 3.045. RS is 0.6 plus 0.609. So then you start solve this one is a cos and tangent inverse 5. So this is a tangent inverse 5 is a 78.6. So cos 78.6. So that will be 0.196 legend. So this is a typical motor we utilize the motor equivalent circuit and we calculate the motor power and motor current. So motor current in the theta side and the rotor side. First problem is that the motor winding is not connected to the any external resistance. And but second one is the same problem. The rotor winding slip rings are connected to the external resistance. So this is the motor slip ring here. We use the slip ring like this. This one we connect it like this. So those are the connected to external resistance. So this is the external resistance. So this external resistance is 3 ohm external resistance. So in this case, we have to calculate rotor current IR. IR we can calculate. So in previous problem, only you got the RR, that's why RR by S square plus HR square. But when you connect the HR resistance, RR by S plus XR is done. So this is the rotor current IR you can calculate. That will be the ER divided by square root of RR by S plus R is done. Square plus 8R square. Then you substitute here. Substitute ER value and those value substitute ER is at 126. And square root of R by S is at 0.05 divided by 0.3 plus 3 over square plus 8R means 0.25 square. So by solving this one, you got the thing with the 39.6 ampere. Okay, this one, and also that we also need to calculate for the rotor current, the rotor power factor. So rotor power factor is equal to cos tangent inverse. So tangent inverse means that this is the RR. So this is the HR by R by S plus R is done. So this one we just cos tangent inverse. So HR we calculate HR value is already given the HR is 0.25. So this one we just 3.166 plus R is done. So this is the 3.166. So then we did 0.996 again. So this is for the rotor. And similarly, stator current. This is the rotor current. So stator current you can also calculate. Stator current is IR dash. So then we use our equation. We use this BS per phase. Here by phase and square root of the formula is you just put the HR resistance. The formula is RS plus TS square RR by S plus R is done. And the square. Plus HS plus HR dash square. So then we calculate. So this is the IR dash is equal to dash by phase is 440. Square root of. So RS value is 0.6. TA is 3.49 square. R by S is 0.05 by 0.3 plus 3 the whole square plus 3 plus 3.49 square multiply with 0.25 the whole square. So by solving this one, we got the 11.11 ampere. So this is for the calculation for the motor. And also that we also calculate for the stator power factor. The formula is cos tangent inverse. So you will 8S plus HR dash divided by RS plus TS square RR by S plus R is done. So this one we substitute here. Cos tangent inverse. So HS is TS we already calculate. HS is done. Rotor Y resistance 3 ohm. So this is 3.045 plus 3 and divided by RS. So RS value is rotor resistance. So RS value you substitute. So 0.6 and KS square is 3.49 49 square. R by A is 0.05 by 0.3. The R is 3. So then you can calculate the distance. This way we just cos tangent inverse 0.154. So this is cos 8.77 or 0.988 lagging. So this is the solution for this model problem. So one case, such case, motor plates are not connected with to the any external resistor. Second case is they are connected to the external resistor. So power transfer is a induction machine, this copy. So induction machine can be they can run as a motor mode or the generator mode. So motor mode takes the electrical power and they produce the mechanical power. And for the generator mode, take the electrical and mechanical power and produce the electrical power. So firstly we talk about the motor mode. So motor mode means that this is for them we set the status power input. The stator power input goes to the stator winding. So then we some power loss in the stator loss. Okay then, so output power is goes to here, P0, and this is the PR. PR means the rotor winding. So this is the rotor winding. The power goes to the rotor winding. So another mechanical power flow to the motor. So this is the PM means the cross mechanical power output. Cross mechanical power output. So this one is go to shaft. Okay, other shafts are this is some law, windage and friction law. And then finally the net mechanical power output. So this is net mechanical power output. So this is for the motor mode. The motor mode, the input is taken from the supply. So this is the stator power input, and some power is lost in the stator winding. So stator power losses, and the output power from the stator, some is power transferred to the rotor winding (PR). So this is the rotor winding power loss happen, and then the some power go to the cross mechanical power output, and they provide it to the shaft. So when the shaft is rotated, it will be the friction between the windage and the frictional law. Frictional law is the shaft is located on the bearing. So when the motor shaft is rotating, so there is a friction between the motor shaft and the bearing. Bearing will be the push bearing or the ball bearing. And also the rotor shaft is moving under the wind, so there will be the windage losses. So final power will be the net mechanical power output. This is for the motor mode. And another one is that we can focus on the generator mode. So motor mode and the generator mode are different. The motor mode is the state that power input, and generator mode is the state that electrical power, but generator mode is the state that mechanical power. So that will be the opposite. Instead of the net mechanical output, for the generator mode, there will be net mechanical power input. And stator power input, there will be the stator power output. So this is the totally different, opposite. So that way this with the stator winding. Okay, this with the rotor winding. And this is the shaft. So this is firstly we go the windage and friction loss. So input power is cross mechanical power input. So input is cross mechanical power input. Cross mechanical power input to the motor winding. So some motor go to the rotor, some go to the stator winding. So that way stator lock. And that will be the output wave then, stator power output. So there are two kind of happen like this. So in this case, we do the two kind of machine. This is for the generator case. Both of the motors are the induction and the synchronous, induction type and the synchronous type. So how does induction and type and synchronous type happen? Induction motor is, this is called as a stator. This stator here, this stator for the winding. So this is the stator winding. Stator windings are put under the floor. So this is the floor winding. Okay, this one is an induction motor. So this one goes to supply, and this is the shaft. So this is the induction motor. Induction machine. Induction machine means we go to the supply to this rotor, the flux are passing through the rotor and rotor will rotate. So this is a stator and this is a rotor. So most of the machines are induction motor and they are construction like this. So this is induction motor. And another one is a synchronous machine. Synchronous machines are stator similar to this stator. So this is a stator winding. So stator winding, so this is a winding. We connect it like this. So this is a stator winding. Okay, so this is stator, the rotor will be like this. So this is the rotor, the two sliving. One sliving connected like this, and this is wire, and another sliving like wire like this. So this is for the Australian bow machine. So this is for the stator. So mostly the generators are constructed like this way. This construction is similar to the induction motor. This is for the synchronous generator or synchronous motor. So this means this construction is similar to synchronous generator. Or synchronous motor. So in this case, this one solutions are supplying as a DC source. So this is DC excitation. DC field excitation. And this one is a winding connected to the output. So this is three-phase winding. Okay, this is for the motor, the stator winding and the induction motor and the synchronous motor. So this is for the power flow diagram. So most of the three-phase induction motor are construction for one, and most of the synchronous motor construction is for the one. So this is for the application of the principle. So now what we do is I will give you the formula to calculate the power power absorbed by the stator winding, power dissipated in the rotor circuit, and mechanical power developed in the rotor resistance, rotor circuit power loss, and mechanical power output. And those are the power and the torque produced by the generator and the motor. So those formulas will be given. So this formula we utilize to analyze and calculate the power flow and power loss in the both induction and the synchronous machine. Next one we set up rotor power absorbed by the ID stator winding here. And also we can calculate for the gross mechanical power output. Okay, this is for the equation for the three-phase motor case. So the power absorbed by the ID stator winding is a P0, 3 multiply ES. ES is stator voltage, IR dash means the root stator current, and multiply with the cos phi r. And the powers are distributed in the rotor circuit. So we can carry 3S, ER, IR, cos phi r. ER is the rotor voltage and the IR rotor current. Or there you can also calculate 3S multiply ES, IR dash cos phi r. So ES is the stator voltage and the IR dash is the stator current. Cos phi r is the power factor of the rotor. And also the mechanical power is PM is equal to PO minus PR. So in this case, PO minus SP0. So PM is equal to P0 and 1 minus S. So this is for the mechanical power output. So we also calculate the power distributed in the rotor resistance. So that will be 3IR square IRR multiplied with 1 minus S divided by S. And also the rotor circuit power loss, you can calculate 3IR dash square multiplied RR dash. And power absorbed by the ID stator winding is 3IR dash square RR dash divided by S. So gross mechanical power output can be calculated. So 3IR dash square RR multiplied 1 minus S by S. And gross torque developed is 3 divided by 2 by NR and multiplied IR dash square RR dash and 1 minus S by S. So those are the calculation of the torque and the power. In this case, you can also calculate the motor speed. Rotor speed at the end slip is equal to the NR is equal to 1 minus S multiplied rotor speed at the no load. So NR is equal to 1 minus S multiplied NS. In this case, S is a slip. So we also calculate the end torque condition. If you know that rotor, the winding resistance, stator winding resistance slip, and the rotor windings are resistance far to the stator side, you can calculate by the torque. So torque is equal to the 3bs square divided by 2 by n0 and slip multiply RR dash divided by S multiply RS plus R dash square, the S square into AS plus 8R dash square. And maximum torque, the formula is a 3bs square multiply S divided by 4 by n0 and multiply with S RS plus RR dash. And split at the maximum torque is SM equal to RR dash by square root of RS square plus AS plus 8R dash square. So those are the formula to calculate this motor power, slip, and torque. Okay, this one is a 440 volt and 4-pole 3-phase 50 half slipping induction motor. Stator winding delta connected, rotor winding star connected. So this is a stator winding here delta. So then we get 440 volt. Here is 440 volt. So this is a stator winding and stator rotor winding star connected. So this is for the ER bar phase. So ER bar phase you can calculate. So this is 218 divided by root 3. So this is the 126 volt. So this is ER and the ES report. Okay, we can also calculate for the KT. KT means the time ratio between the stator voltage and rotor voltage. So KT we can calculate. So then we get ES phase divided by ER phase. So then we get ES per phase 440, ER phase 126. So then we 3 by 4 line. So this is the KT we can calculate. So to calculate this we want to calculate the maximum torque and the slip. So So firstly you need to calculate for the maximum split. Sm, so Sm is equal to R dash divided by Rs square plus As plus AR dash square. So this is for the split at the maximum torque. So firstly you calculate for the R dash. So R dash formula is Kd square multiplied with RR. So this is rotor resistance multiplied with the turn ratio square. You got the stator rotor resistance far to the stator side. So this is equal to 3.49 square multiply 0.05. So you got a 0.610. And similarly HR dash. So that will be Kd square multiply HR. So that will be the 3.49 square multiply 0.25. So that will be 3.050. And we also saw that the split at the maximum torque. The formula is RR dash divided by square root of RS square plus 8S plus 8R dash square. So then you substitute here. So this is R dash 0.61. Square root of RS. RS means theta winding resistance. So 0.64. 216 square plus 3 plus 0.5 square. Then you call this a split. So that will be 0.1. The maximum split is 0.1. And after that, you got the maximum split, you can also calculate for the torque. So maximum torque. The maximum torque formula we already calculate. Torque maximum is 3Vs square and 3Vs square divided by 4 by and 0 and split divided by S into 4 by n. This one should be the 4 by n. Just change. So 3Vs square is 4 by n 0 as S multiplied R dash divided by S into Rs plus R dash square, and that's also the S square multiplied AS by HR dash square. So this is the formula you got this one. So in this case, this one is that we also utilize for the maximum torque. So maximum torque is that we use the equation. So in this case, we also connected to the stator resistance of phase. Point is O. So this is that we substitute. So that way we use T maximum. T maximum is 3Vs squared divided by 4 by and 0. Okay. So this formula is also the square root. Either we use this formula. So all the 4 by n square S into R dash divided by Rs square. So this is the S into Rs plus R dash square plus S square into 8S plus 8R dash square. So now you substitute here. 3S is supply voltage of 440 square divided by 4 by 3.1416 and 3. So 1 of 3 you can calculate. 1 of 3 and 0 is 25 because of the MRC and 0 you can calculate. And 0 is equal to frequency divided by P by 2. So frequency is 50 Hz. So how many number of 4 by 2? So 50 by 2 you got a 25. So because of this one, this is 25. And 3 is 1 and the R dash. So R dash we already calculate. R dash is 0.61. And square root of 3 is 1. And RS is 0.6. Plus R dash. So R dash is 0.61. And 3 square is 1 square. And AS. AS with we calculate the AS. So there will be the 3 plus 3.05 square. So by solving this one, we calculate the maximum torque 277 Newton meter. So this is for the calculation for the motor slip and the torque by using the two motors the calculation formula. I mean,